Molecular orbital theory. So what is this molecular orbital theory? This basically is another theory that explains how bonds are formed between two atoms. Okay, so molecular orbital theory simply is an extension of the quantum model that we have seen in previous chapters. This theory states that atomic orbitals of different atoms, they combine to form molecular orbitals. So if hydrogen is making a bond like this, so ignore this, let's say if one hydrogen atom and second hydrogen atom, they make a bond and they become H2 like this, hydrogen gas. So how are they going to combine? The atomic orbital from hydrogen and the atomic orbital from the second hydrogen, they are going to combine and they will form something that is called as a molecular orbital. Okay, so previously the orbital theory was like, valence bond theory was like, okay, hydrogen's 1s1, this is 1s1 as well. Their orbitals, if this is s spherical shape, they will overlap with each other, right? And the electrons would be found somewhere in the middle. This is called valence bond theory. But valence bond theory cannot explain every single type of atom. There are some exceptions that valence bond theory was not able to explain. So those exceptions can be explained by molecular orbital theory. So molecular orbital theory says there is no overlap. They do not overlap. The 1s from one, this 1s from one of the atoms and this 1s from the second atom, they will combine and they will form something that is completely new, that never existed, and this is called as molecular orbital. So that's the difference. This is atomic orbital because it was one atom. This is the second atomic orbital, and these atomic orbitals, they combine and they give you a molecular orbital. How are these formed? The term that we use is that these are delocalized over the resulting molecule. So the electrons, basically these orbitals are delocalized, their location. Based on that, the electron density, it is delocalized and it is arranged like a molecular orbital. Okay, so when these atomic orbitals from different atoms, they combine, they can combine in two different ways. Okay, what are those two ways? Either they can combine and they can form a molecular orbital which is called as bonding molecular orbital, or they will combine and what we get is called as anti-bonding molecular orbital. So these are the two types of molecular orbitals that can exist. When they combine additively, meaning when the addition is happening, when they combine, additive combination of these atomic orbitals results in constructive interference and a bonding orbital is formed. What does that mean? For example, if you take two waves, if this is a wave and I have another wave, when these two waves will combine with each other, there are two ways that they can combine. One is if they overlap with each other perfectly, then what you get is a bigger wave. Okay, and that is when this kind of addition or combination is called as constructive interference or additive combination. So when they add each other's effect, they enhance each other's effect, that is called as bonding molecular orbital. Okay, whereas the second way is when these two waves combine with each other but they are actually opposite, they are combining in opposite directions of each other, they will combine and they will cancel each other's effect. Okay, that is called as a destructive interference. Okay, so that is called subtractive combination, when they subtract each other's effect. When subtractive combination of atomic orbitals occurs, you get destructive interference and the orbital that we get is anti-bonding. Okay, for example, this is 1s orbital from 1, this is the second 1s orbital. When these two 1s orbitals combine, if they undergo constructive interference, they combine good, they give you a better orbital which is called bonding molecular orbital. How is it better? It has lower energy. Lower energy, that means it is more stable. It is comparatively more stable than either of these 1s. Now this molecular orbital is even more stable and it has lower energy. How do we show or represent bonding molecular orbital? It is represented as a sigma or a pi. As long as it's a sigma interaction, remember sigma and pi bonds, it would be called as sigma bond or pi bond. Okay, But when these orbitals, for example like this, when this 1s and 1s they combine in a destructive manner, they give you what we call as anti-bonding molecular orbital, and you get these regions where you can never find electrons. So it is not an enhanced region, it is actually a reduced region. Why is this reduced? Because it is less stable, and it has more energy. So it has higher energy than either of these, and that is why it is less stable. And these are called as anti-bonding. And how do we show them? We basically show them by putting a star on top. Okay, so if it is a sigma bond, we show it as sigma star. If it is a pi bond, we will show it by drawing a pi star. So the difference how we represent between bonding and anti-bonding is bonding is written like sigma or pi, anti-bondings are written basically with a star. That just means they are less stable, they have more energy. Okay, that is what is explained here. Electrons in bonding molecular orbitals are stabilizing and they have lower energy. Electrons in anti-bonding molecular orbitals are destabilizing and they have higher energy. Okay, and then how do we show this? We usually draw a molecular orbital diagram that shows us what orbitals are present and how many electrons are present in each orbital. Okay, for example like this is 1s orbital of a hydrogen atom, right? This is 1s orbital of second hydrogen atom. When they combine with each other, they form, this is an atomic orbital, this is also atomic orbital. When they combine with each other, they give you molecular orbitals. Okay, how? Again, remember, one orbital from one atom and one orbital from the other atom are combining. So total, how many orbitals are combining? Total, we have 2 orbitals. So when 2 orbitals combine, how many should you get at the end? You should also get 2 orbitals at the end, 2 atomic orbitals combine. So at the end, we should make 2 molecular orbitals, and that's what we are making here in the middle. So these 2 will combine and they will give you 2 molecular orbitals. One is called bonding, which you can see here in the bottom, and one is called anti-bonding. Bonding orbital is lower in energy. This is the graph of energy. Energy is increasing as you go from bottom to top. So the energy of bonding is less than either atomic orbitals, right? That is why we draw it at the lower region. Anti-bonding has more energy, so that is why we draw it up here. And you can see it's written as sigma star and this is written as sigma. Okay, so this is molecular orbital. And this, what we have, all of this is called the molecular orbital diagram. It shows us how many orbitals are present, how many molecular orbitals are present, and it shows us how many electrons are present in each of them. Okay. Now we'll look into how these are actually formed. Okay, so how can you make these orbital diagrams? You start with, for example, I want to draw a molecular orbital diagram of hydrogen. So I would write the electronic configuration of hydrogen first. So what is the configuration of one hydrogen atom? It should be 1s1, has 1 electron. So if you draw the orbital diagram for 1s1, s has 1 orbital, meaning 1 room, 1 square, and it has 1 electron, so it would look like this. Okay, so this is 1s1, and that is what is drawn here. This is the atomic orbital of hydrogen atom. Then, because it is H2, you have a second hydrogen atom, so these are the 2 atomic orbitals. You first draw these orbitals and draw the number of electrons that are found in them. Then you combine them. How will they combine? Remember, they will combine always to give you 2 different types of orbitals. The one which is lower is sigma, the one which is higher will be sigma star. So this is bonding and this is anti-bonding, and I am starting with 2 orbitals, so I should end up with 2 orbitals, right? So I should get 2 orbitals at the end. Now we have to fill electrons into this. How will we fill electrons? This is 1, this is the second one. So total number of electrons is 2 electrons. So I have to divide 2 electrons between these 2 orbitals, these 2 molecular orbitals. Now, how will we give the 2 electrons? You always give electrons first to the lower energy. Then if you have more, you will give it to the higher energy. Okay, so the same process that we have learned earlier in electronic configuration, the same thing occurs. The low energy gets more electrons. First, if it's filled up, then you move on to the next one. And remember, in one orbital, maximum number of electrons is only 2. So that's what we are doing here. This is sigma S, and this is also sigma S, right? Because they are coming from S. So this can hold 2 electrons. So 2 are gone, and this stays empty because I only have maximum 2 electrons. So that is called the molecular orbital diagram for hydrogen. This way you can draw the orbital for any other molecule. Okay. Example. Before we move on to next example, we'll look into another couple terminology that is used when we learn about molecular orbital theory. First one is called bond order. Okay, what is bond order? Bond order is given by the formula. Bond order is number of bonding electrons minus number of anti-bonding electrons divided by 2. That is the formula for bond order. Okay, what does this tell you? Bond order gives you information about stability of the bond, which simply means if you have a higher bond order, the bonds will be stronger and shorter. Okay, a bigger bond order simply is a number. Okay, so if you have a higher bond order, meaning the bond is stronger and it will be shorter. Okay, most of the times, if the bond order is 1, that means it's a single bond. If the bond order is 2, that means it is a double bond. If bond order is 3, that means it's a triple bond. Sometimes these bond order can also be fractions, which is normal. Okay, so they can be fraction, which means it's telling you there is a resonance present. Okay, now if the bond order is 0 or it is less than 0, then your bond is unstable, which means this bond is not going to form. No bond will form. Bond order has to be at least a positive number for it to be forming. If it is 0 or it is negative, it means this bond does not exist. This molecule is not stable. So this molecule will never form. Okay. Another couple terminology that is used is called paramagnetism or diamagnetism. Okay. Paramagnetism are those materials that are weakly attracted to the magnetic field and they contain unpaired electrons. Okay. They have, how can you know if a compound is paramagnetic or not? They will contain unpaired electrons and they will always be weakly attracted towards the magnetic field. Okay, diamagnetic atoms are the ones that, or materials are the ones that have no unpaired electrons. They have no unpaired electrons. They are not attracted to the magnet. Instead, they are actually slightly repelled by the magnet. Okay, how and why would you have to know this? We will try some questions. We'll draw molecular orbitals and the question can simply ask, does it have any unpaired electrons? Okay, so you look at the orbital diagram and you see if it has unpaired electrons or not. Or it can ask you, is it paramagnetic or is it diamagnetic? So how would we know? If it has unpaired electrons, it's para. If it has no unpaired electrons, it is dia. Example, oxygen is actually paramagnetic. Okay, and nitrogen is diamagnetic. So let's see, how can we actually figure that out from molecular orbital diagrams? Okay. All right. So we just drew the bond molecular orbital diagram for H2 earlier. Let's figure out what is the bond order of this H2. Okay, what is bond order? Bond order was, remember the formula was, bond order is number of bonding electrons minus number of anti-bonding electrons divided by 2. What are bonding electrons? That are found in the bonding orbitals, the ones without the star. Okay, how many electrons do I have in bonding? 2. So it is going to be 2 minus, how many electrons do we have in the anti-bonding? None. So 0 divided by 2, which gives you 2 over 2, which is 1, which tells you the bond order between H2 is 1, which means what is present between the 2 hydrogen atoms in a molecule? It is a single bond. So that is the significance of finding the bond order. It tells you what type of bond exists between these atoms. Now let's try how the questions would look like. Draw molecular orbital diagram for Li2. Li2 simply means I'm drawing it for lithium 2. Diatomic molecules, that is majorly what the questions would look like. You would not be asked anything more than a diatomic molecule. Okay, so 2 atoms at max. Which means, how will I draw it? I first need the configuration of each of the atoms. I have 2 lithium atoms and I need only valence shell configuration of these, because only valence shell participate in bond formation, right? So where lithium is how much? Lithium is 1s2, 2s1. But I only care about this 2s1 because this is the outermost orbital. So this would be 2s1. Let's draw 2s1. This is the second atom, also 2s1. When they will combine, this has 1 electron, this also has 1 electron. When they combine, how many orbitals are combining? 2 orbitals are combining. So how many should I get at the end? Also 2 orbitals. So we will get 2 orbitals at the end. 1 and 2. The one with lower energy will be bonding. The one with higher energy will be anti-bonding. So we show anti-bonding by drawing a star. How do I know this is sigma? Because these are s orbitals. Whenever s orbitals combine, remember they form sigma bonds. They are always hybridized. Whenever the orbitals are combining, overlapping, they form these sigma bonds if it is combining along the nuclear axis, right? So now how many electrons on the left side? 1. How many electrons here? Also 1. So total I have 2 electrons. So I'll start giving them 2 electrons. 1, 2, because first I fill the low energy. I have nothing left for the high energy and I'm done. That is lithium 2. Okay. Now if I ask you what is the bond order will be number of bonding electrons, which is the electrons that are present in the bonding orbital, which is right here. So 2 minus in the anti-bonding, which is 0. So it is going to be 2 minus 0 divided by 2, which is 1. So if this molecule exists, what would be the bond between the 2 lithium atoms? It is going to be one single bond. Okay, and you can see it's drawn atomic orbital 1, atomic orbital for the second atom, and this is the molecular orbital, bonding, anti-bonding. Okay. Now, if these were the smaller atoms, right? If we have another atom, kind of like bigger atoms, when you have bigger atoms like nitrogen, boron, carbon, oxygen, which also have p orbitals in them, then how do they combine? Their molecular orbitals would look something like this. Okay, for example, for B2, C2 or N2, the molecular orbitals will look like this. For O2, F2 and Ne2, the molecular orbitals would look like on the right. What is different in them? Okay, for example, let's say if I want to write the orbital diagram for carbon. Okay, what is the electronic configuration of carbon? 1s2, 2s2, 2p2. Right, so it has, what are my valence shell electrons? These are my valence shell electrons. So 2s2 and 2p2, which means s has 2 electrons here and s has 2 electrons here. The second atom, right? There are 2 atoms of carbon, remember. So this is 2s2 for one of them. This is the 2s2 for the second one. This is 2s2 for the first carbon atom. This is the 2s2 for the second carbon atom. When they combine, s will also combine, and there are also p orbitals. So how many orbitals are present in p? 3 orbitals. Remember, we always draw 3 orbitals for p. So that is what is drawn on this side, 2p. That is what is drawn in for the other atom as well, 2p. How do these p orbitals combine? The p orbitals combine in these manners, what is shown here. Okay, so sigma, there are 2 different arrangements. This is basically px, py, pz. If you remember this, there were 3 orbitals, one along the x-axis, one along the y, one along the z. Same here, px, py and pz. When these atomic orbitals combine, they can combine to give you sigma bond and pi bonds. Okay, so when they combine along the axis, remember p is like this, 1, 2, and the third one is like in the z axis. So when the atoms will combine, only one of these p orbitals, right, like this, will be able to combine along the axis of the atom. The other will have to combine around it, around the axis. So that is why those will be pi bonds. So when one of these and one of these will combine, they'll give you the sigma bond. Okay, what is this? 1 and 1, so 2 orbitals. So how many sigma you get? You should get 2 sigma. So one is this sigma and another one is sigma star, bonding and anti-bonding. And when these two and these two will combine, they combine as a pi bond. So you get 2 from here, 2 from here, total 4 orbitals. So you can see here, this is 2 here and this is the other 2 here. Okay, so this is pi and this is pi and this is pi star. Okay, so basically when they combine the orbitals, total orbital in p is how many? 3 here and 3 here, so total should be 6. And you can see this is 1 2 3 4 5 6, so you get, at the end you get 6 orbitals. It's just that 2 of them are sigma and 2 of them are in pi form. Okay, now what is the difference between the two diagrams? Let me erase all of this so it becomes cleaner and it makes more sense after this. Actually, we will let this be here for now. I'll not erase it. Okay, the differences, you can see the differences in the order. Okay, this, whenever p combines, this is pi, sigma, pi star, sigma star. So in this case, the order for p orbitals is pi, sigma, pi star and sigma star. And remember, sigma is always 1 and pi's are 2 orbitals each. Okay, whereas on the right side, the difference is, it is, the order is different. The order is sigma, pi, pi star and then sigma star. Okay, so these middle ones are the ones that are flipped and that are different. Okay, so just remember this order. You do not have to memorize the order or the chart. You just have to remember the ones on the left side basically are going to be for the elements where the atomic number, their z, is less than 8. So when z is less than 8, you follow this. When z is greater than 8 or equal to 8, we follow this. Okay, so boron, carbon and nitrogen, all of them, their atomic number is less than 8. So that is why we follow the left chart. Starting oxygen, oxygen is number 8. So oxygen, fluorine, neon, for all of them, we follow the chart on the right side. Okay. All right, so again, remember, see this again, the difference. I just want to make it more cleaner here. It's cleaner. So let's look at this again. The difference is, this is pi, sigma, pi star, sigma star. Whereas this is sigma, pi, pi star, sigma star. So the major difference lies between these two orbitals, the bottom ones. This one has pi in the bottom and then sigma. This one has sigma in the bottom and then pi. That is the major difference. Okay. Now the question is to draw the molecular orbital diagram for C2. Okay, let's finish that off. Carbon was 1s, 2, 2s, 2, 2p, 2. We care about valence electrons, so we draw these. This is one of the carbon atoms. This is the second carbon atom. And I will follow the left map because it is C2. Okay. Now, carbon will be 2s2 and 2s2. And it will be 2p2 and 2p2. So when we follow this carbon, I have to put 2 electrons here and 2 electrons here. And remember, we always give electrons 1 to each of the orbitals and then we pair them up if we have extra. So that's what I'm doing here. This will have 2 electrons here and this will have 2 electrons in the 2p orbital. Now when they combine, you combine one of the orbitals at a time. Okay, so how many electrons are in this orbital? 2. How many are here? 2. So total is 4 electrons. So I have to distribute 4 electrons in these bonding and anti-bonding orbitals. Okay, so I'll go 1, 2. First I pair this all up, then I go high energy 3, 4, and I'm done. Okay, next we have to move on to p orbital. This has how many electrons? 2. This has how many electrons? 2. So total is again 4 electrons. I have to give 4 electrons in all of these p orbitals. How will I give them 4 electrons? Again, you always give the electrons to the lowest energy first. I will give electrons to lower energy, and if I have more, I will then move on to the higher energy ones. So 4 electrons, I go 1, 2, and I can pair them up 3, 4, and that is it. I'm done. I cannot add any more electrons anywhere. Okay, so that would be the molecular orbital diagram for C2. Cleaner, without any of these arrows and lines and dashes that you're seeing, but basically the number of electrons. That's it. Okay. Now, if I ask you what's the bond order for this, bond order will be all the number of bonding minus number of anti-bonding divided by 2, right? So let's count how many are bonding. Bonding are the ones without the star. Okay, so these electrons are bonding. This is a bonding electron, right? And this is anti-bonding. This is also bonding electron. There's no star on these, right? So how many electrons do we have here? This is 2 electrons. And this is total of 4 electrons. So in the bonding I have how many? 4 plus 2 total 6 electrons. Minus anti-bonding. This is the only one with the star. Anti-bonding, that is 2 electrons. Divided by 2, so total is 4 divided by 2, which is 2. So what is the bond order between C2? Here it is 2, which means it is pretty stable bond. Okay. Let's try one more example. Okay, this time we'll focus on drawing the molecular orbital diagram for oxygen, O2. Okay, first thing we have to decide which side. Should I use the left one or the right one? Oxygen's right here, so I'm going to go on the right one, which means we can get rid of the left. Okay, now if we focus on the right, first we need what is the electronic configuration of each oxygen atom. There are 2 oxygen atoms here, right? So we have to find what type of bond is this. What is the bond order? What is the molecular orbital? Okay, so what is one oxygen? Electronic configuration 1s2, 2s2, 2p, 4. Okay, so the electrons that I want to focus on are valence, so only 2. So I need 2s2, 2p, 4. So this is going to be my 2s2, 2p, 4. 2s2, 2p, 4. This is one oxygen, this is the second oxygen. Okay, now this has 2 electrons, so I'll go 1, 2. This also has 2, so 1, 2. P has 4, so 1, 2, 3, 4. This P also has 4, so 1, 2, 3, and 4. Okay, that's total 4 electrons each. Now we have to use these electrons and fill our molecular orbitals in the middle. Okay, so this has 2 electrons here, 2 electrons here. Total is 4. So I need to give 4 electrons in my molecular orbitals in the bottom. Okay, so I'll go 1, 2, filled up all the way, then 3 and 4. Now I have all 4 electrons here. Done. Next I move on to P. This P has how many? 4 electrons here, 4 electrons here. Total is going to be for this 8 electrons. Okay, so how will we get these 8 electrons? We start from the lowest energy, which in this case is this sigma 2p. So we go 1, 2, then I go 3, 4. Remember, don't pair them up. You give 1 each, right? So 4, 5, 6, 7, 8. That is a total of 8 electrons. And this is the molecular orbital diagram for oxygen. Now let's do the bond order. Bond order is number of electrons in the bonding minus number of electrons in the anti-bonding divided by 2. Okay, so which electrons are in the bonding orbitals? These are bonding, and this is also bonding. Which ones are bonding? The ones without the star. Remember that. Okay, so how many here? This is 2, this is 2, and this is 1, 2, 3, 4. So total 4. So total is 4 plus 2 plus 2, that is 8 electrons bonding. Now which ones are anti-bonding? The only anti-bonding that is present is this with the, oh no, there are 2. This has a star and this has a star. So there are 2 of these. This has how many? This has 2 electrons here and this has 2 electrons here as well. So total is 4. So 8 minus 4 divided by 2, which gives you 4 divided by 2, which gives you 2. So what is the bond order in this case? 2, which means oxygens have a double bond between each other. And if you remember from Lewis structure, it does look like this. It has a double bond. So molecular orbital theory gives you the same information. Okay, let's try one more example. This time we are working on nitrogen, N2. I'll just go a little bit faster here. Nitrogen, I need electronic configuration 1s2, 2s2, 2p, 3. So this is my valence electron. Now which one to use, left or right? I will be using the left one because this is N2 less than 8 atomic number. Okay, 2s2, 2p, 3. This is my first nitrogen. Then I have a second nitrogen, 2s2, 2p, 3. So we'll give first 2 electrons here. So 1, 2, 1, 2 for this one as well. Total I have is 2 here, 2 here, so total is 4. So I'll go 1, 2, 3, 4. This p has 3 electrons, so it will be 1, 2, 3. Same here, 1, 2, 3. Now this is 3 electrons here, 3 electrons here, total is 6. So I have to give 6 electrons in the middle. So I'll go 1, 2, 3, 4, 5, and 6, and I'm done. Okay, what is my bond order? Total bonding is this without a star, this is without a star, so 4 here and 2 here, which gives me total 6, minus, oh sorry, this is also without a star, right? So 2, 4, and 2, total is 8 electrons. Okay, all the electrons without a star are bonding. So 2, 4, 6 plus 2, 8. Minus how many are anti-bonding with the star? This is the one with the star, which is 2 electrons. So minus 2 divided by 2, which gives you 6 divided by 2, which is 3. Which means the bond between the nitrogen atom is a triple bond. Bond order is 3. And if you draw the Lewis structure, you would see that the Lewis structure actually looks like this. So molecular orbital theory also tells you the same. Triple bond exists between 2 nitrogen atoms. Okay, that is molecular orbital diagram. You can practice all these molecules, okay, and these are the examples given to you, okay, final answers, so you can solve them and then figure out if your bond order matches, if your diagrams match. So please practice them on your own and compare your answers. How will I ask a question? Exactly like this. I will give you the 2 diagrams. You do not have to memorize the order. You just have to know which one to use when and how to draw it. Okay. And again, we will only focus on homonuclear atoms. There could be 2 different heteronuclear, for example, nitrogen and oxygen. What's the bond between these? We are not going to focus on that in this course. Okay. Next thing, I could also ask you a question about ions. For example, draw the diagram for O2 minus, not O2, O2 minus. So draw the molecular orbital diagram. Then it is asking, is it stable or not compared to oxygen? We just did oxygen. Bond order for oxygen was 2. So we have to find what is the bond order for O2 minus and if it is more than 2 or less than 2. Okay. Is it paramagnetic or diamagnetic? And is the OO bond in peroxide shorter or longer than oxygen? Okay, let's see. Okay, so let's draw the electronic molecular orbital diagram for O2 2 minus. O2 2 minus, I need 2 atoms again. So there are 2 atoms of oxygen here, but it has a 2 negative, so I will equally distribute them here. You can distribute them odd as well, like one will be 0 charge, one can be oxygen, other can be oxygen 2 minus, either or, it doesn't make a difference. But usually we try to keep it symmetrical, okay? Your final answer will not be different, that's what I mean. But it is O minus and O minus. Okay, what would be the configuration of O minus? So this is O minus, O minus, O with a negative charge. What is the electronic configuration of oxygen? 1s2, 2s2, 2p, 4, right? That is when we have just oxygen. If it is O minus, that means I have 1 extra electron, so it would become 2p5. That is O negative. So it is 2s2, 2p5, 2s2 and 2p5. So we add 2 electrons here, so 1, 2, 1, 2. 5 here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. That's 5 electrons in each. Okay, now we will give these electrons into molecular orbital. This total is 4 electrons, so we go 1, 2, 3, 4. This is 5 here, total 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that is total 10 electrons given away. Now we find the bond order. That is molecular orbital diagram for O2 minus. Bond order will be all the bondings. Which ones are bonding? This is bonding, this is bonding, this is bonding. Okay, so 2 electrons here, 2 electrons here, 2 here, total 4, 4 here, total 8. 8 are bonding, minus total non-bonding. How many are non-bonding? This is non-bonding, 2 here and 4 here. So total 6 non-bonding. Okay, so 8 minus 6, and then divided by 2, which basically gives you 2 divided by 2, which is 1. So what is the bond order here? 1. Now the question, if you remember, was asking, is it more stronger or more stable than oxygen? No. Bond order for O2 was 2. Bond order for O2 2 minus is 1, which means this is oxygen is more stable, this is less stable. More the bond order, higher bond order means more stable. Okay, so the same molecular orbital diagram that we drew is drawn here. Bond order was 1, so it is less stable. Less stable mean it will be more reactive. Okay, now the question was, is it paramagnetic or diamagnetic? How do we figure that out? For para or dia, we are going to look at, does it have any unpaired electron? These electrons are paired, these are paired, these are paired, 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 and paired. Every electron is paired, which means there are no unpaired electrons. When there are no unpaired electrons, that means it is diamagnetic. If in any other example, let's say there was one electron that was not paired, it was by itself, single, then you would say that this is paramagnetic. Okay, and that is basically molecular orbital diagrams.